Calculating the electric field from a given charge distribution can often be tricky and involve challenging integrals. Gauss's law gives us a way to avoid that by calculating the electric field for charge distributions that are highly symmetric. The three different symmetries that we'll look at are cylindrical symmetry, planar symmetry, and spherical symmetry. Using Gauss's law, shown here in the yellow box, involves 5 different steps. The first one is identifying the symmetry of your system, which we've already done. The second one is choosing the appropriate Gaussian surface. For cylindrical symmetry, we're going to choose a cylinder that is radially symmetric with the line of charge. For a plane, we're going to choose a box or a cylinder, it doesn't matter, but just something that is perpendicular to the surface and goes through both the top and bottom of the surface. And for spherical symmetry, we're going to choose a sphere that is also concentric with the actual distribution of charge. The next step when using Gauss's law is to determine how much charge is enclosed by your Gaussian surface, and you can do this using the associated charge density for your given object. For our cylinder, which has a charge density of lambda, we only want to count the amount of charge that is inside this Gaussian cylinder, which I am now coloring in orange. We can find that simply by taking our charge density, which is charge per length, and multiplying it by the length of the cylinder. For our planar symmetry distribution, we want to find the amount of charge inside this portion of our box. Again, we have a charge density of sigma, which is charge per area, so to figure out this amount of charge, we simply multiply charge density by that area. And lastly, for our spherical example, we have a sphere that has a charge density of rho, and so the charge inside our Gaussian sphere is simply just rho times the volume, which often is actually just going to be q, where you're told that this sphere has some charge q, and q is going to be what's inside the Gaussian sphere. Step 4 is to determine the flux through your Gaussian surface, which is going to be working with this left-hand side of Gauss's law. For our cylinder, we only have flux through the curved portion, so our flux is going to be E times the area of just the curved part of our cylinder, which is 2 pi r L. For our planar symmetry, we have flux going through both the top surface of our box and the bottom. So our fluxes is going to be E, whatever the electric field is, times this area plus this area, because we need to take into account both this upper and lower portion. For our sphere, we have flux going through our Gaussian sphere, and so the actual equation for fluxes is going to be our electric field times the surface area of our sphere, which is 4 pi r squared. At this stage, all that's left is to take what we just found and plug into Gauss's law. So we would plug in whatever we got for Q inside on our right-hand side, plug in whatever we calculated for flux on our left-hand side, and then simply solve for E. And in effect, what we will have done is to determine the electric field at this given distance away from our actual distribution of charge.